Hi. It's going to be in English, not French, so if you can't understand English, I'm sorry. Okay, I'm Paul Sandoz. I'm going to talk about the Stream API. I hack on OpenJDK, work for Oracle, and for the last year I've had lots of fun implementing streams and playing around with Lambdas and doing a bit of jigsaw-y stuff on the side and all sorts of other interesting things in the OpenJDK. I don't expect you to read that. What it means is don't place bets on what I say, even though I'm talking about stuff that's now released. I'm not talking about stuff that's in the future. I'm talking about stuff that's in the past. But that's the way it goes. So the goals of this presentation is to introduce the Streams API and what it's about. But I think if there's a really big meta goal, it will be to say that you can get an IDE, get JDK8, and you can start playing with it now and start understanding by getting your hands dirty and playing with the IDE and getting a feel for coding using the Java 8 features in the Streams API. That's what I'd like to try and really get across. So I'm going to teach you a bit about the API and what it can do, and so to also get across that this is the first of potentially a few performance optimizations that could happen in the future. So I'm going to be showing benchmarks. I hope to get through all of them. I don't know. If we don't, I'll have a vote for the ones you want to see, and we'll see how we do. But the idea is this is the first of many optimizations that could potentially happen. So if you look at things, most of the code you write using collections, it's all very loopy. You don't have much choice, all for loops, iterators and so forth like that. And it's really sequential and it's imperative. That is not necessarily the programming model du jour if you look at all the functional programming out there. We want to sort of move Java along gently in that direction and help process this type of information in a more functional manner, a less sequential, a less imperative manner, and that's what streams are about, with a little or a big help from Lambdas. So it's really an abstraction for specifying aggregate data. It's a view over your data. It's really quite simple in that sense. It sort of looks at your data as a view over it, and then you can transform based on that view. And it can be infinite, like iterators and so forth like that. And the key thing is it ups the level of abstraction about what you can do. So if you can do that, then you can start monkeying around all the way under the covers and start doing some interesting optimizations and fusing laziness. But the really key thing we can do once we up the level of abstraction is go parallel, which I call map reduce in the small. Okay, so the Stream API is what I would say is the first of, I hope, many good Stream-like or Lambda using APIs in JDK8. We needed to showcase what Lambdas can do. The Stream API does that. It has a particular model for how you use it, but it's not the only model out there. There's other Stream-like abstractions that you might have known already, like RxJava or what Akka does and so forth like that, or even distributed streams. So it's not the only one. If the interface doesn't match what you need, you can choose an interface. The key here is there's important functional-like patterns you might see over and over again in these different Stream-like contexts. Map, filter, flat map, reduce, and stuff like that. They might be named slightly differently, but we'll start to see more of these patterns in JDK8 and in libraries that use JDK8. So I'm going to sit down because I can't type standing up. I don't know why. My brain doesn't work like that. It takes too much power for me to stand up and type. So I'm going to talk and go and explain a little bit about the stream anatomy and pipeline. How many people know a little bit about streams? Have you seen some presentations? So a fair bit. Whoa. Did you go to Jose's presentation? Okay, so I expect he's done an excellent job, which means I can talk about some other stuff, but let's just have a quick go. So I'm going to be using IntelliJ, but as NetBeans and Eclipse each have Java 8 support in them as well, and I'll make sure that I'll scale it up like that. So here's a very, very simple stream. What it's doing, it's counting words greater than a length of 4, strings that are greater than a length of 4. It's very, very simple. It's very readable. You can see that in a for loop too. There's probably not much difference between the two, but I'd argue that this one is more descriptive in what it's actually doing. Where do we get the words from here? If we look at our words, I'll just hide that. It comes from a list. So what we've done was added the stream method on there. And stream method is essentially a default method on collections. I guess if you went to Jose's talk, you're familiar with default methods. We've added new methods to collections, and this is where it gets the stream. And the stream is coming from something called a splitterator, which I'll just say this for a moment. If we've got time, we'll get into more detail. It's like a souped-up iterator It's on like an iterator on steroids, and each of the collections we have supply their own split iterator, and we construct streams from a split iterator. And this is a key thing that allows us to split things up in many different parts and then operate on them in parallel. Okay, so it's pretty simple. I can just run that. I won't get very exciting output out from it, but we'll get a number just to show you that it works. Okay, we get 94 words coming out greater than 5 letters in there. But let's just have a quick look at what count is. I'll just dive into the code. So count is a method that is composed of a map and a sum. So we can copy that back there. So we've got filter, map, and sum. And what we're doing is we're mapping each of our words greater than 4 characters to 1, and then we're summing up all the ones. So that's actually how you do a count. You transform your model, you transform your problem into another domain, and then you can operate on it. This is often a trick you can do with the stream APIs. You think, well, how the heck am I going to do that? Well, you can sort of transform your problem. So what we're doing is transforming it to a long stream consisting of a bunch of longs, and they're all just ones, and then we just sum up the ones like so. And what is actually sum? If you look at the implementation in here, sum is, sum is a reduce. So what we got is filter, map, reduce. Map, reduce in the small. You can do it in the large with Hadoop, and you can do it in the small with streams. It's the same concepts at different scales. And in fact, if you look here, this is, anyone know what that is? Method reference? You know what it is? So if I was changing this, it actually consists of a little lambda, oops, I can't even type sitting down now. Like so. It's essentially that, but if sometimes I prefer using method reference. It's actually more readable sometimes. The code is more descriptive of what's going on. There's often a choice between using method references or lambda expressions, and it's up to you, but sometimes it increases the readability of your code. So that's exactly the same. So what's going on here? There's essentially a source of our stream, which is our list. It's actually an array list underneath. And then we have a bunch of intermediate operations. And these operations are lazy. They don't actually do any work. All they do is set up the description of what to do. So we pass in behavior, and the behavior is based on the lambda expressions we pass in here, like the filter and the map. And then the last one here, the reduce, is what's called a terminal operation. This is the one where it triggers all the work. It triggers execution of the pipeline. Once we do that, things start working. And we take our recipe up, we fuse all the ops together, and we push the elements through. And all the elements get through to reduce, and it all sums up nice and easily. Now, if we look at a more literal view of that, this is what we can sort of break it down. So if we split that out, this is what you wouldn't normally do this, but it's instructive to see how it's composed. We get a stream of words, then we filter those words, and we convert them to ones, and then we count. This is a very linear pipeline. If I was going to operate on the filter words after I've transformed it into ones, like we just do, get me all the distinct versions. If I run that now, waiting for it to run, I get an exception. I get an illegal state exception. What this means is we can only operate on a stream once. We can't branch or fork or anything like that. It's just a linear set of operations going forward. If you try and operate on filter words after you've transformed it into ones, you get an exception. If you do the same on the ones itself, after we've done the reduce operation, the terminal operation, let's just say convert to boxed, and run it again, we get the same exception. You can't, once you've consumed the stream, you can't do anything. You have to go back and start again and do the same thing again. So it's not in the same sense like RxJava, where you'll be forking and branching and merging back together. And it's a very simple conceptual linear pipeline that's a one-shot operation, essentially. Okay. So let's go something a little bit slightly more complex, but not much. What happens if we want to reduce all those words that we had to one big string and concatenate them comma separated. So if we want to do string combined words like so, we would get our words as before, get a stream view over it, like so, and do the filter as before. And we can do our reduce. And this time, what we want to do is sum up our strings. We want to comma separate it. Like so. Do you think that will work? Yes, no? Is there any, can anyone see anything wrong with that? Let's run it. Okay, so we get our words out, but we get a rogue comma at the front there that we don't want to really have. What reduce is doing, it's saying, give me a base value as a starting point, then use that for the first value of A, and B will be the first element in your stream, and after that, keep going, like so. We could do something slightly different. Instead, use a form of reduce that doesn't take an initial or base value. If we get an error here, what we have to do is convert it to an optional, like so. Because we don't give it an initial or base value, it means the stream could be empty, which means we don't have a result. So we have to encapsulate the concept of no result or some result, and that's what actually optional does in the streams here. So we could do this, get, or we could do optional, or else, if it's empty, we could return another string, just call it empty, 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 like that. And we can run this. We should get a slightly different result without the comma in before. Okay, we get no comma now. If I was going to up that to 100, now you might recognize where those words come. There's probably no words greater than 100 characters in Shakespeare, so we get the empty instead. Okay? Now, that all works out quite well, but there's another problem with this. It's not actually particularly very efficient. You know, when you concatenate strings together like this, you're adding lots and lots of strings. What's actually happening here is something called a fold left. Here's how it's grouped. When we're using the base value, we're taking our empty string, we're appending comma to it, then we're appending A, then we're taking all that, then we're appending comma to it, then we're appending B, and so forth and so on like that. And if you do string additions like that, that's going to use up lots of memory copying here. The performance will suck. It's not particularly very efficient. And that's an interesting argument for why persistent collections won't necessarily solve this unless you design them very, very carefully, because persistent collections will have similar issues in terms of dealing with stuff like this. So one way to actually do this instead is to use something called collect. And collect is the mutable form of reduce. It is a Java-friendly way of reduction using mutable stuff that we already have in Java, like array list and so forth like that, or string buffer, string builder, and we can just do something like this. I'm using a static import from the class collectors, but we have a joining here, so we can do collect joining and separate it with a comma like this. Notice that I don't need to worry about what the base value is. I just specify what I want to join with, and that should actually run fine. And we won't get the comma out, we get the same result as before. Did that actually work? Sorry? Sorry, I can't hear. You have to shout up. Oh, thank you. This is great when I do interactive. People tell me what's wrong. There we go. So we get it back again. So if you're going to do this with strings and that, use the collectors. If you're going to do reduction with integers and longs and stuff like that, reduce works fine. Doubles works fine. But if you're going to do things with lists and that, you need to look at the collect and the collections, which is a mutable reduction. So one of the things I want to get across here is when you do this, you notice it's a sort of it was all a sort of fold left with all the brackets going towards the left. But if the reduction operations that we have are associative and at initial value is a base value, what we can do is we can shift where the brackets are and we can change the grouping. So instead of it all shifted to the left here, we can balance that out. As long as we don't change the order of the terms here, we just change how things are grouped, we can group things together slightly differently. So we could have one group here and one group here, and then we can take those separately and operate on them concurrently. And that's where we get our parallelism from. As long as you play by certain rules, we can split the problem up, operate it concurrently, and merge all the results back together again. And that's the key thing here. And collectors allow you to do that as well, and it hides much of that under the covers, so you don't need to worry about it. Okay, let's just go for a slightly more complicated example. I'll just walk through this quickly. Here's an example just to get across what you can do with streams and what we've added to the API. Very simple grep files. Grep for all things that smell and look like Lambda expressions in this little project I've written. So what it will do is it will walk through all the files in my source project here as a stream, because you've added a method to files called walk, which returns me a stream of paths recursively in the directory. And I want to take that, and I want to filter all the directories. All I want is regular files. Then I want to filter the files named with Java. Then I want to flat map those files and get all the lines out of those files. I want to open all those files up and get each line from the file, and then I want to filter the line that contains something that might be a Lambda expression, and then I want to print it out. Don't worry about that red. That's IntelliJ. It's not understanding Lambda expressions as well as it should. So let's just run that and see if it works. And then I'll explain the flat map in a bit more detail. So we get some output here from all the source files we have. Now the flat map here, I'm sorry to say we made a mistake in the API. The files.lines is another stream method we added, which basically takes a path, opens up the file, and then turns me a stream of lines coming out. But we chose to return an I/O exception instead of an unchecked I/O exception, which makes it difficult to handle in flatmap, because flatmap takes a function but doesn't throw any exception. So we have a sort of a little bit of a friction going on here, which is annoying, but we can't change that now. So I wrote a wrapper, little wrapper method that does the files lines and refroze it. It's not as pretty as it can be. We're going to have to try and fix this. There's a potential way down here to fix it. See me later if you want to talk about it. I don't think I have time, but general point, exceptions and lambdas are actually a tricky thing to get right. The EG actually punted doing it properly to have more time to think about it and get it right next time around. Okay, so that's basic introduction. Let me go back to the slides. Okay, there's many ways to create stream sources. I showed you a few just there, from a list, from files. You can create them from arrays, or you can go deep down and create them from split iterators. I'm going to skip through all this for the moment. Let me just talk about this. There's a bunch of stream sources. They have properties about how well they decompose, how well they split up. Things like ArrayList are very good at splitting up. Things like linked list are not, because you're dealing with 1, 2, 3, 4. They're all linked. To work out what the end of a linked list is, you have to traverse the whole of the list. So it's very hard to split up, whereas an array list, you know its size, you know the middle, you know the quarter, and so forth like that. Hash set is reasonably good. So they all have a certain set of properties, and they have a certain set of characteristics about what they are. Like an array list is sized, an iterator is not sized, and so forth like that. You can use these properties to sort of intuitively work out whether something might be performant or not when you're iterating over it and working in parallel. That's a point I want to get across here. So things are lazy. Those intermediate operations like filter map are lazy. Some parallelize better than others. We'll get into that a bit later on. Some are stateful, like sorted or distinct. You can't sort things until you have all the data you have, and then you have to work on the sort. Distinct needs to keep a hash set of things it's seen to work out whether something should be removed from a collection or not. There's a bunch of characteristics that can change as you go and manipulate through the pipeline. So if we start with an int stream range, then our characteristics of our pipeline, we know its size, we know it has this particular order, it goes from M to N. We know each element is distinct, and we know it's actually sorted. But if I do a filter operation, we no longer know the size, because we're removing elements from the stream. We don't know whether the filter we don't know enough about that lambda expression to say, at compile time, to say whether it will remove something or not. If we map, we lose the distinct and sorted characteristics. And if we go unordered, an explicit thing, we lose our order. We're saying, I don't care about order anymore. You can re-inject these characteristics back into the stream so we can say we're distinct, and now our stream is distinct again. We can say we're sorted. We can actually limit, which means it still doesn't know the size. I don't have time to get into that, unfortunately. And then we can say peak, which doesn't do anything. You can use that as a debugging operation. It's interesting to sort of understand a little bit about what these things do, because these characteristics are how we actually can optimize the pipeline when we go parallel. So something that's sized and ordered is different from something that's sized and not ordered, or something that's not sized and ordered. We use these things, little tricks we do to optimize what we're going to do. And there's a bunch of terminal operations I showed a few with collect and reduce. And they have a bunch of characteristics, like limit would be a short-circuiting operation, as would be something like any or match all, or find me the first or find me any are short-circuiting. Okay, let's go a bit into the rules of the streams game and go back to the IDE. So let's see if we can work out what happens here. So I'm getting my words again as before as a list. And what I'm doing is a for each. And I'm actually adding the word from the list back into itself. It's a rather silly thing to do. What do you think happens when I run this? Will it run out of memory? We're going to get an out of memory exception, or out of memory error. Okay, let's see. I get an exception, but I get something, I get what's called a concurrent modification exception instead. If you've ever done iteration and you've tried to modify the collection while you're iterating, you will see exceptions like this happening. What we've done to all our collection implementations is we've added checks in, to ensure that if it's going to be self-modifying, it will throw as quickly as it possibly can based on the constraints of the implementation. It's called failed fast. That's always been there with iterators. What we wanted to do is make sure that that same behavior there was there with collections. You cannot modify or interfere with the source of your collection while you're actually executing the stream. So that's sort of rule one of the game here. It's a pretty standard rule. Get more into the rules of the game with state. And state is important because things change when you go parallel. So let's just start with a sequential stream and gently introduce parallel stream here. So let's look at what this is doing. We're going over our words, stream of words, we're filtering again, and we're collecting it to a new list. Like so. Actually, that is not what I wanted to do. I've got the old code here. Let me revert it back. What I want to do is FWS to add. In fact, we can change this to a method reference, like so. So what I'm doing is I want to create a new list of the filtered words, like so, and print them out. So we should get some output 94 as before. Okay, so if this looks fine. It's okay sequential. This is fine sequential code. And it's okay to do so. But you have to be aware of the hazards when you actually go parallel. So I'm actually turning my whole pipeline into a parallel pipeline in terms of execution. When I do the for each now, things will start executing in parallel rather than in sequential. So what happens is that these little lambda expressions, method reference will get called concurrently instead of on the same thread that I called this pipeline on. So what do you think happens here when I do the for each? There'll be multiple threads coming in and adding to this. This is a concurrency catastrophe, as I call it. Let's see what happens. So we get 91, 92, 94. Well, did it get one right? Not quite. Sometimes you even get an exception. Let's see there. Oh, we got an exception. That's because we're doing something we shouldn't do, is that using the list, the array list, in a concurrent manner. That's bad. So I'm not saying that using for each and parallel is bad. It's just that if you're doing this in parallel streams, you have to be careful and you have to know a bit more about what you're doing. So the right thing to do is what you saw the code before, is do the to list instead. And that protects you from these concurrency hazards. And instead we just comment out that. And that will give us our list, and it should be stable. Now, the other way you could do it is not through the collect. If you really wanted to do so, you could use the collections.synchronized list. I get my scrolling right. Like so. Again, IntelliJ showing an error there when it actually shouldn't. Oh, no, it's actually correct. I'm not. Thank you. I'm blaming the tools when I shouldn't. It's okay, so that will actually produce a consistent result because now we're synchronized. So which one do you prefer, the collect or the synchronized list with the for each? I would argue the collect is actually better. Also, the collect will do something that for each doesn't do, which will preserve the order of the elements in the list. What's happening here is that the threads will get called, and whenever an element is ready in whatever thread, it will get called with a for each, and the order will be different because parallel introduces non-determinism. You can play around with this, and you'll see the results. I encourage you to do so. So here's another aspect of state change, which is a little bit more complicated. So what I'm doing here is I'm using a set to try and emulate, try and create a distinct stream. So I want to do a filter and say, if I haven't seen this element before, carry on, then I want to add the element to that seen hash set afterwards, then I want to collect a list. Now I know there's another way of doing it. It's just for explanation purposes, I could just do scene.add with filter, and that's fine. But I want to get the point across. There's two separate operations here working in tandem with each other to try and make the list distinct. And I'm using a linked hash set to show order. So if I run that, in sequential we should see that things are the same. The two sizes of the scene hash set is 168 elements. The linked list the list we produce is 168 out of 260 elements, and they're the same to be or not to be. That is the question. So what happens if we go parallel here instead? So remember, the filter will get called concurrently, the peak will get called concurrently. So we get, one is saying 169 elements in that hash set, but look, there's only 1, 2, 3, 4, 5 in there. Again, concurrency hazards happening here. So we could make that linked hash set collection.synchronized again, and synchronized set. Where is it? There we go. Like so. Do you think that will improve matters? Will that make it work? No? Yes? No? And those are correct because we will see there's different results coming out. Even though it's reduced the concurrency hazards, there's still a race between the filter and the peak here. But what we're trying to emulate is a stateful operation. What we should do is just change to distinct and do away with these two here, and then we're done. We don't have to worry about all this other stuff, and then we can run it and we should get the correct result, 168 coming out. So what I want to try and get across is there's rules of the game here. If you want to make sure that at some point your streams are written sequentially, and some point in the future you may want to go parallel, you don't have to, but if you do, then be careful about how you're writing the streams. To be aware of, if you go parallel, you might get different results if you don't sort of build up your pipeline in a way that's amenable and it doesn't have concurrency hazards. Okay, back to the slides. So there's the rules of the games in the slide. Just to say, there's always an exception to the rule. And if you might have recognized this already, the for each doesn't return anything, so it has to do something by side effects. When I was doing a for each adding to a list, that's a side effect. A peak is a side effect. There is side effects. Be careful of these methods with side effects when going parallel. Okay, so why would you want to go parallel? It's really one thing, and that's to get results faster. But maybe. That's the thing. There are many chips and many cores. We try and keep them hot. There's even something called Project Sumatra, which is doing stuff on GPUs and SIMD. And just to point, that's something that's actually really, really happening. That was this change set 7 weeks ago to OpenJDK Sumatra, which is making modifications to the Stream API to execute this stuff on GPUs. This is someone from AMD, I think Eric, doing this stuff. So this is actually investigative research work, looking at streams, not to execute them on the VM using the hotspot and the JIT, but to try and offload that onto a GPU which has thousands of cores rather than on my laptop, 2 or 4. So this is very interesting work. And it's not something that we're just saying is possible, we're actually investigating. Yeah. So the key thing here is do not always assume parallel is faster. If you're playing around with streams, do not put parallel in your code everywhere in production code. You're liable to run slower. You need to think about this a bit more. It's easy to do, but not always the right thing to do. We've given a sort of powerful thing to the developers, but you have to use it with care, with great responsibility. What's that Spider-Man quote, I think? So what's going on under the covers in parallel? We use something called fork join library. And fork join is great, but it's pretty low level. So we've upped that level of abstraction. Underneath, we hide all the fork join stuff for you, and it uses it under the hood. So going parallel almost always uses more work. It always takes more work to do, and it's not a magic bullet. I'm just saying again, it's not always faster. I'm trying to drill this in. And there's many factors which will affect performance. The size of your data, how things split up. I showed you array list splits up nicely, whereas a hash set not so nicely, an iterator not so nice at all. Are you sharing cores of other applications? If you can use primitive streams, use those over boxed things because boxing hurts. I will get to that later. We've made it explicit and unobtrusive. It's very simple. Sequential is a default. If you want to go parallel, you say parallel on your stream. And the whole pipeline is parallel, not what was before it or what's after as it affects the whole pipeline. Okay, so let's have a quick look at that. See if I've got time to explain this. So here's something very, very simple to explain what's going on under the hood. I have some nice, pretty animations that I showed at DevOps Belgium, which is online. You can see those in parlays, but I decided to go the opposite route and try some ASCII art instead in this one. We'll see how well it goes. So what I'm going to do is I'm going to create a stream of integers from 0 to up to, but not including 128. I'm going to box them, but I'm going to collect them in a map. And what I'm going to do is I'm going to map each integer to the thread, the name of the thread that integer was processed on. And I'm going to group them into a map. This is collect grouping by. It says map each element to a key, then all the elements that map to the same key, collect them up. And by default, this will collect all the things up into a list that map to the same key. So I'm actually peeking underneath the covers, underneath the hood of what's going on in the Stream API. So if we run this sequentially, we shouldn't get anything interesting. We just get the main thread. Nothing surprise here. We get the main thread here, and it goes all the way through, ordered up all the way to 127. Now, if we run it in parallel, like so, we should get something different out. And it's actually quite instructive of what's actually going on here. So if we look when we run it in parallel, we can see we're definitely running fork join threads. We're using the common fork join common pool, and we have, how many of these are running? 1, 2, 3, 4, 5, 6, 7, 8. That's the parallelism on this laptop, it's 8. And if we look at the actual elements here, each thread gets a different set of elements to actually work on here. And if we look at the level of granularity, it seems that our granularity is 4 elements at a time. We had 120 elements in our range, and we're processing chunks of 4 elements. That means we split things up into a tree of 32 nodes at the bottom, sort of a binary tree going down, and each of the nodes gets 4 elements. This corresponds essentially to one fork join task, and each fork join task gets 4 elements to work on. And we see that they get slightly different numbers of work to do, because that's the way the threads, sometimes threads take a longer time to warm up and schedule and so forth. That's so some get some warm up faster and get more work to do. But also threads will still work from other threads if they're doing work already and there's work in the queue. So that's why we see this uneven distribution. I have 8 threads on my system. We over provision to balance things out a little bit better. So just this simple thing actually shows quite a bit about what's going on underneath the covers. If we look with, if I try and explain with this ASCII art, I don't know how well you can see this. I'm not sure if it's going to be successful. This is the bottom left tree of the first 4 nodes from all the way up to 16 nodes. Say if the first one was on thread ID 1, the second on thread ID 2, third on 2, third on 1, and they get processed. And when each of these nodes gets processed, it creates a map of the thread ID name to the elements in the list, because there's only one key going here, and same and so forth. Now we've got all the nodes here. When we want to go up one level, we have to merge these together. We have to merge 2 maps together. So we have now a map of 2 keys, each with distinct keys. And we want to go up one level again, and when we merge the maps. And now here's where something interesting happens. What we do is we have a key conflict, so we merge the value in the right into the left, and we merge the 8, 9, 10, 11 into, appended onto 1, 2, 0, 1, 2, 3. And you notice that's how we keep the order. We noticed that it was all ordered, all the way up. It was always increasing numbers. That's how we maintain and counter order in the system, is by going up and merging the right into the left as we go up the tree. I encourage you to have a play with this. It's quite educational to see what's going on underneath the covers. Now, we get this question asked a lot. What about web applications and parallelism? The best thing you can possibly do is disable parallelism when you're going through web apps, because your web apps are designed for processing lots of requests. They're not necessarily designed for processing streams in parallel when you write code. If someone's written a web app with a parallel stream, it's really best to actually disable a level of parallelism in a common pool by default, unless you really know what you're doing. So you have to set this system property, which is what application servers on Java 8 should actually do, or web servers should do. So if we actually run this one, we won't get any parallelism out. We'll just get it on our main thread, like so. You can do a trick if you want to actually control a little bit of the parallelism. At the moment, we don't allow any control of the parallelism and the resources yet. We punted the problem to solve later on and went for the simplest solution possible, which is to use the common pool. If you want to control the degree of parallelism, you can create your own fork join pool, and you can submit your stream within a fork join task. And it just so happens that things wire up the way the thread context, thread locals work, and so forth like that. The context it works, I will execute this in this fork join pool and not in the common pool. So if I run that one instead, I will only get 2 threads going. So there are ways to control it, but we need to do a better job. Okay. So parallel execution is greedy. It will use as many resources as it's available to it, essentially by default in the common pool. So we can't actually configure it, as I said. We need to refine this in a future Java release. The obvious solution seems appealing. Just specify the parallelism you want in the parallel method, but I think that's wrong. We need to think about this more. Perhaps in the future, the runtime should work out the best possible mode of execution dynamically, like the JIT works out how to compile the code efficiently. What if we could, after n sequential executions, gather some stats, some timing, and then try speculative parallel execution? If that performs, keep doing that until it doesn't perform anymore. That sounds simple to say, but that's actually quite hard to do. So we need to do some more work on that. Okay, I'm going to go into some performance now using measurement examples using a tool called JMH, which was written by some of our performance engineers in Oracle. It's an open source benchmark tool, which is very handy. It allows you to essentially, your hotspot is very dynamic. It will do stuff that you don't necessarily know what it's doing to optimize code, which makes writing micro benchmarks very hard. If you use a tool like this, it will help you isolate those differences so that you can more accurately measure stuff correctly. There's a link there. So I've got 6 to do. I'll do 1. I've only got 10 minutes left, so we can have a vote. See if you want to look at some others. So I'm gonna talk about really 2 things here. There's 2 concepts to working out whether when you're going parallel, whether you get speed up or not. One is the number of elements you have that you're operating over, and one is the cost per element. So let's have a quick look at this. I will skip that for the moment. So let's look at the map of sum and int and look at the code. So I've got a little JMH benchmark here. It has a bunch of annotations that says how it's measured. What I'm setting up is an integer array of certain values. And then I have a benchmark for a classic for loop, looping over the array and doing a simple calculation. This is where, so the size of the array is n, and this is the cost q that I refer to here. Now if we look at the benchmark for the parallel stream, we're creating a stream over array, going parallel, and doing exactly the same calculation here, and then summing it up. So that our Q is essentially multiplying the value by 5 and then adding together. It's a very, you can imagine that the Q is very, very low. The cost per pipeline, cost per element is very cheap. And the same for sequential, but without the parallel here. So do you think, if say I had 100 elements in this array, do you think the parallel would be faster or slower? Slower, most definitely. If I have 1 million elements in there, do you think it would be faster? Still slower after 1 million. Let's have a look at results. Okay, so this is the results I got on a Dell laptop. I downclocked the CPU. I was told to do that because no one understands what hyperthreading does. So you downclock it, so hyperthreading doesn't mess around with a parallel execution. So you can it makes apples to apples more easily. So what we have here is a speed up over the for loop. And in the blue line, we have the sequential stream. And in the green line, we have the parallel stream. And what happens is often you'll see this classic S-curve in these low Q cases. So what happens is that the sequential stream, at about maybe 1,000 elements, the cost is comparable to the for int loop. We can't compete with for loops, unfortunately, just yet. We can almost with iterators, but we can't do it with primitives and for loops. We're not taking for loops away. If you want real performance in that, you can use the for loops too. But you see that it ramps up to 100% at about 1,000 elements sequentially. So we get to that. But it takes always more work to go parallel. The cost of splitting, cost of using fork join, the cost of scheduling these threads has a fixed cost. We're fighting Amdahl's law. So it's going to ramp up after, I think the crossover is between 10,000 and 100,000 elements. We get a crossover point. I think it's 200 to 400 microseconds per execution. I need to talk to Lexi Shiplev. He has all these details about the exact crossover point we measured. But once we get over that, we start to hit our 2x. We get to 1 million elements here. So you've got to watch out when going parallel. It's not always a given. You have to have the right situations to get your speed up. Okay, I have 6 minutes left. Which one do you want me to go into? I got the boxing, Monte Carlo calculation of pi, probable primes. Probable primes is a high Q, low N problem. It's the inverse of the in-stream one. Any votes? Boxing? Megamorphic. You want to do that one? Okay. Any others? Megamorphic it is? Okay. I missed the fun one, the Monte Carlo one. I'll see if I get to that one later. Let's go megamorphic. Skip my... Okay, let's just go to the code. So this is actually a fairly easy one to explain. So we've got a bunch of benchmarks going parallel and sequential. I'm doing an array of streams parallel, but I'm doing 4 map sum, like so. I'm doing it same for sequential and parallel. I've got 1 mapper. If I have 2 mappers, like so, I can do mapper 1, mapper 2. I'm basically alternating the instance of the map function on the stream pipeline. And I can do it for 4 as well. Each of these expressions result in a separate instance of a map operator, in a sense here. Now I'm doing on the 4, 1, 2, 3, 4. So if I measure the results of this, how do you think it will compare? Do you think they'll all be equal? Do you think it will be a gradual, linear slowdown? If you know how hotspot works, you might know the answer already. I see someone smiling. So look, you might just seen the results here. So blue is sequential, green is parallel. So if I have the number of mappers is 1, I get this result. I get almost 2x speed up. Smaller is faster here. If I move to 2 mappers, I get exactly the same result. But I move to 4, bam, I get a slowdown because hotspot can't optimize that as efficiently as I'd like it to, and others would like it to. This is what will happen in lots of code, not just particular to streams, but it's the way the type profiling works is it can only deal with a certain number of type profiles before it bombs out. So that is actually a problem that Cliff Click talked about in 2001 in April in a blog. It's well worth reading. Inlining is not happening at the crucial points that we need to do, and things are not getting optimized, and it's a hard problem to solve, and we've got some more work to do. This is what I was talking about, the optimizations that will happen in the future. We're doing some now with the parallel execution of streams. We've got more work to do to make sure streams are efficient both sequentially and in parallel. Okay, I have 3 minutes left. I think I should make some time for some questions, if you have any. Unfortunately, I don't have time to do Monte Carlo Pi right now. I can do it afterwards in a small group if you want. But any questions? Nope. Question at the front here.
Yes, I had a question about your very first example with the sum.
Okay.
And I think actually there's type inference going on to choose the version which takes a long. Is it because the type is declared as a long, or?
This one here, map to long.
Yes, but the first version that you had was using sum, and actually the IDE suggested the long version.
Let's, you mean I had this here?
Yes.
Okay. So why isn't that working? No, I had a count. Like that. And count was composed of a map to long and a sum. Is that what you want to look at? So let's go and have a look there. So that was the composition.
Right. So I was wondering if it's only because count returns a long, or is there other versions?
No, we only have it longs because we don't want to overflow on ints, because a stream might be, even though collections can only contain a max of int max value minus a certain amount, not much. We want to ensure that things can go larger in the future, so we don't want to bind ourselves to the restrictions in size, because the arrays 2.0 work in the future might actually have larger collections, which is a good thing, I think.
Thank you.
1 minute left. Okay, no questions. Thank you very much. Oh, there's one at the back. Oh.
It's too